actually... Okay, I'm going to get started. Well, can you guys in the back hear me okay? Alrighty, cool. So I was thinking, because I haven't really gone over this in detail and demonstrated it for you guys, as a reminder, our first packback discussion closes this coming Sunday night, just before midnight. I've been seeing some good discussion topics pop up in here already, so good job you guys who have posted these. These are all excellent. I do actually, I guess, you know, there's a lot of people taking this class. We're going to run out of big picture things to talk about sooner or later, although if you think of something you do want to post, like, always feel free to do it. But now that we're getting into the new reaction material from chapter 14, I was actually thinking that people would also be posting a lot of questions that are more, I guess, reaction specific. So things like, you know, why does this mechanism work this way? Why does the regiochemistry work out to be Markovnikov versus anti-Markovnikov, that sort of thing. So I actually just posted this in Canvas, so probably you might not have had it be noticeable yet, but so open-ended questions are better, like what do these reactions have in common? Why is the charge distribution the way it is? Something where someone would actually have to write out like at least a sentence or two to answer your question instead of just like a quick sentence fragment of like, use this reagent, or here's how you name it, that sort of thing. So I'm kind of trying to get discussions going rather than just someone being like, here's the answer, bleh. So that's going to be much more difficult if you can't include images. So in terms of posting chemical structures, unfortunately there is no image hosting on Packback itself, but I included a link of how do you add an image to your post. Basically, you need some sort of account on a free image hosting site like Imager. And then if you've got ChemDraw here, which hopefully you guys do because we have a site license for it. If you don't have ChemDraw, let me pull that up real quick because... So if you, I guess, are taking this lecture at CU and you took OChem 1 elsewhere and you haven't used ChemDraw, which I think there's a handful of people in that situation, what you want to do is go to our OrgChem site, go to Lab Courses Software, and go get ChemDraw, or like hand drawing it is totally fine too if you've got a tablet, if you just want to sketch some stuff out. If you want to straight up do it on paper, take a photo, post that. Basically whatever method works best for you to get a photo or structure or whatever into the post that you're trying to talk about, because that'll make it a lot easier to say like, here's what I've got for the mechanism, what am I doing wrong, where do I go from here, why does this arrow look like this, just that sort of thing where an explanation from another person is going to sort of push the discussion along instead of just ending it right off the bat. Okay, so I probably am not going to go through the whole step-by-step thing of doing a ChemDraw image. Oh, actually, I guess just to finish this up. Okay, so here's just some stuff I did in ChemDraw. If you are using ChemDraw to post images, you can do File, Save As, and then you can save it as any one of the file structures that they listed on this page. So JPEG, PNG, GIF, any one of the standard file formats, but not the ChemDraw file itself. So the default file structure is something that ChemDraw is used to opening on its own. But you have a lot of choices here. I don't know if TIFF's okay, but here JPEG is, oops, I guess bitmap. You can do JPEG and save it, and then it'll complain about data loss because once you save it as a JPEG, ChemDraw won't be able to reopen it, but then you can host it on whatever image site you want, and then you can upload that. Okay, so I guess going back to the community feed, as a reminder, so I'm kind of hoping that every person will post either a question and 2 responses or just 3 responses. So we don't have to have like, I guess there's a total of about just under 300 people taking the course, so we don't have to have 300 questions a week. Like if you just want to have like 3 responses to other people's questions that really piqued your interest or got you thinking about something, then that's totally fine, and we can have like a long discussion thread after like some of these questions, because some of these are really thoughtful or are really like detailed, thought-provoking questions, and you know, basically I'm just trying to get so you don't have to, you know, come up with content that you don't particularly care about just to get something out there. I'd rather have like, you know, if someone posts something that actually piques your interest as something cool, then by all means feel free to have a back and forth about it, and then that would be your 3 posts right there. Question in the back?
If you like are reading through a question and some responses and you have a follow-up question, is that question then considered a question or a response?
I'll consider it a response. I think like Packback is determining questions as like the initial like parent post kind of in the forum, and then like all the discussion in the thread after that is like a response. So yeah, really, I'm thinking I'm just gonna, like they divide it up by like initial post versus response, and I'm thinking I'm just gonna like, so long as you get 3 things of any sort during a given week, that's good enough for me, just so you're like staying engaged like to some level or another. So. And also as a heads up, if you are doing sort of low content posts of like just, you know, responding like yes, or something like that to someone else's post, like that I think tends to get weeded out unless you like elaborate further, like yes, and also you can extend this to cover this other situation or something like that. Basically like include more content of your own to push the discussion along if you want it to sort of count towards your 3 post thing. Okay, so I guess any other questions for you guys? Yeah. I know, I'm trying to get that turned off. The tech TA is being a little bit slow right now, so yeah, sorry about that. Yeah, hopefully later today, like they've tweaked the instructor side settings a little bit over the past semester, and yeah, we'll see. Sorry guys. But yeah, I'm hoping that we can just retroactively give everyone their points back. Okay. Other questions about this? Okay, cool. Okay. Alrighty, so I'm going to get back into the lecture material. So last time we covered up through nomenclature and structure of alkynes. So today I'm going to get into addition reactions of alkynes. Okay. And And for anyone who has missed, I guess, all of last week so far, just a reminder here that lecture capture and notes are posted at orgchemboulder.com, and then you can just go to the drop down for my lecture. Okay, so that's kind of what I'm lecturing off here. All right, so at the end of lecture last time I covered the difference between terminal and internal alkynes. Basically, terminal have at least one H attached to them, internal just have a couple of R groups on either side. We're going to be looking at terminal alkynes because, just redraw that up here. Terminal means they're at the end of the molecule. And this is because this is the only way to tell Markovnikov versus anti-Markovnikov in the reactions we're going to do, because this is the only way to get a more versus a less substituted side going on. Okay, so most of the reactions that we're going to do in this chapter are pretty much, maybe not identical to what we did with alkenes, but they're very, very similar. So here, that's... So that's a terminal alkyne. So these reactions are so this is actually going to serve as kind of a decent partial review of the alkene chemistry from OChem 1 if you're feeling a little rough on that. The difference is alkenes had just the one pi bond, so we could add stuff to them once. Alkynes have two pi bonds, so we can do an addition to them either once or twice, depending on how we set things up. And then there's some other weird stuff that's going to change as sort of a consequence of that. And we're not going to cover every reaction that we did to alkenes, just because some of them turn out not to work as well for alkynes, sometimes for reasons that have to do with like how nucleophilic the pi bond is. But we're going to cover the ones that are reliable enough to sort of be used in synthesis, for example. Okay, so we're actually going to start pretty close to where we started with alkenes, and that is adding HX. So HX addition. So if you remember, actually I do it the alkyne here. Okay, so here's an alkyne. If we react this with HBr, and I'm just going to do the overall reaction for now. I'll do the mechanism afterwards. What we're going to do is get rid of one of the pi bonds, add an H and a Br to the two carbons of where the triple bond used to be. Is this Markovnikov or anti-Markovnikov? Markovnikov, good. So that means that my bromine is going to add to the more substituted carbon, and my H adds to the less substituted carbon. So okay, so in case Markovnikov style is ringing a bell, but you don't quite remember what that means, basically it's just the more substituted carbon gets the good stuff that's getting added during the reaction, so the bromine in this case, and the carbon with the H on it gets another H. Okay, so that's going to get us to, we've lost one of the pi bonds, but not both of them now. And let me actually also mention something else about this. Okay. So we've added a H onto the less substituted carbon and a bromine onto the more substituted carbon. One thing that we do actually have to be a little bit specific about here is that we're only adding one molecule of HBr at this point. So we would actually have to specify one equivalent, because if you remember, if it's written on the arrow, that's implying that it's present in molar excess unless we specify otherwise. So if we just say HBr on the arrow, we're going to assume it's just going to add as many HBRs as it can. So we can actually show that happening as a separate step, where if we do another thing of HBr, one more equivalent, or a second equivalent in other words. And again, we're going to add Markovnikov style. The more substituted carbon just keeps getting more stuff. Like now it gets a second bromine. and the carbon with the H's gets one more H. Okay. So questions about that one so far? Yeah.
For shorthand, can we just write HBr over 2 equivalents?
You absolutely can, yeah. So I'm drawing this out like showing the stop at the partway point. But if you want to go all the way to the single bond here, you can just say either 2 equivalents, or because at that point it's using excess HBr, you can just leave it non-specific and either that or just say HBr excess and just have it go all the way to the end. Okay. So that's the Markovnikov style addition. Do you guys remember what we would want to add if we were trying to do this anti-Markovnikov style? Yeah, exactly. So So again, if we want to show it stopping part way, we're going to have to specify 1 equivalent. And now we're getting the opposite regiochemistry. We're getting the bromine added to the less substituted carbon and the H added to the more substituted carbon. Okay. And again, if you want to keep going as a separate step, so ROR and HBr, another equivalent, is going to get you all the way to this thing. All right, so you may be looking at this and wondering which side is the more versus less substituted carbon, because now they each have one non-H thing on them, but the regiochemistry ends up working out so that it's still like this one is considered more substituted as far as addition goes. All right, so this reaction is actually a bit less selective though. It's a little bit hard to stop after 1 equivalent addition just because with the radical initiator, it tends to get a bit carried away and sort of maybe add 2 HBRs to one molecule and none to another molecule. So this one is not as useful as it's written. You can actually force it to stop after 1 addition by adding so I have a specific version of this in the notes, but something along the formula of 4 R groups on a nitrogen with a plus charge, and then a bromine or halogen counterion. So this is called a tetraalkyl ammonium salt. I don't remember if we're going to cover these later on, but these end up being pretty useful for tweaking a lot of solubility things in reactions. If you're having issues with solubility, a lot of the time these will actually help overcome that and get your molecules to mingle with each other, even if they wouldn't normally. So I think that actually will do something about, yeah, I'm not entirely sure how it changes the mechanism so that it stops partway, but this will actually favor just the single addition of HBr. Okay.
Can you do that for both of those or just for those?
For the Markovnikov step. So I think it's actually now that I think it's primarily for the single, or for the Markovnikov style. It might also be for the anti-Markovnikov because I think I've seen it for that as well, but I think it works better up there. So I guess for our purposes, let's just say it works for either one. Welcome. Okay. So in terms of mechanism for this, I guess any other questions on this overall?
Is the carbon the more
Good question. So really it comes down to like why this carbon is more substituted comes down to when you're doing the mechanism, where is the radical that you form going to be best stabilized? And having it be on a carbon with another methyl coming off of it, if you guys remember, like these have some carbocation kind of like qualities to them. And it turns out carbon is going to help stabilize that radical better than bromine does. And so it just comes down to this ends up, actually no, that's, yeah. Okay, that's correct. Okay, so you end up stabilizing the radical better here so that this one holds the radical and then it can go pull the H off of the HBr. Okay, so in terms of mechanism for these, we can go through sort of a similar process to how we did for alkenes, just we're doing it twice. But we can actually sort of pause and look at how being part of an alkyne originally is going to change things from the alkene. So the mechanism for the Markovnikov style one. All right, so if you guys remember, this is going to start out with a pi bond going out, getting protonated, and kicking out a halide. Which is going to get us to here. And then, just like always on the alkene, bromine can come in, attack there. And then we end up with that. Okay, so this is just stabilized by where the R group is sort of stabilizing the carbocation best through hyperconjugation. Okay, things get a little bit more interesting when we look at the second edition because when we start doing the same thing again onto the double bond that we just made, we're going to go through this step, and in this case, having a full-on positive charge on this carbon. In the past, we've always just stabilized that by hyperconjugation, like the R group is doing what it can to send some electron density towards it, which is better than nothing, but here, having the actual bromine with lone pairs on it and a full positive charge means that we can actually send some electrons onto the positive charge through resonance. So like this. So we would not be able to do this with a radical just because there's not as much you can do to stabilize the radical with the lone pairs on bromine, but with the positive charge, bromine can totally help out. And the benefit to doing this is that now you have a form where everything has a full octet. So here's so this is actually easier to do this reaction once you've already done it once than it was to do it the first time. Okay. So pretty much the same mechanism as before, just there's a couple of interesting things to notice as we go along and sort of go through it the second time. Okay, so questions about that? Yeah? Oh, it does. Sorry. Yeah, I sort of skipped that step. But yeah, from here, you would show it as, depending on which resonance form you wanted to show it happening on, you could either just show the Br minus come attack the carbocation there, which would get you to the product, or if you're doing it to this resonance form, you would have to show it still going for that carbon, but then those electrons go back onto the other bromine because they're not needed for resonance anymore. Yeah, sorry, good catch. I didn't draw in the entire rest of the mechanism. Okay, and then I saw, yep.
So if on a test we're asked to show the mechanism, do we show the resonance portion or not?
You can. I guess I'm more doing it as sort of an explanation of why this is a little bit easier the second time through. But if you just showed it with the carbocation, that would also be okay too. Okay, so other questions about this one? Okay, cool. All right, so that's one kind of analogous reaction that we've seen before, but now we're doing it twice in a row. The next one we're going to look at, or the next two that we're going to look at, also involve regiochemistry, so we're adding an H and a not H, but something weird happens along the way that changes things. Okay, so we're looking at hydration here. So we're going to be adding an H and an OH. So there's several reactions we saw in this category for alkenes. We saw acid catalyzed hydration. We saw oxymercuration reduction. Those are both Markovnikov style. And we also saw hydroboration oxidation, which is anti-Markovnikov. So okay, so we're going to be looking at a few different ways of doing this, adding an H and an OH. But there is something very important now that's going to change. And that is, so after one addition, we're going to get to a functional group that is interesting enough that it actually has its own kind of name. So just like for HX, we do the addition once. We get to something that, and I'm going to leave it vague as to which side is more or less substituted by showing this on an internal alkyne, I guess. Okay, so we do this on an alkyne. Actually, staying consistent with the notes, I'm going to put a couple of H's on the end just so it's symmetrical. Okay. So we start with an alkyne. We do the addition once. I'm leaving it very vague as to how we're doing that because we'll cover the details in a second here. But we get to something that looks like this, where we've added an H and an OH. We have a double bond here. So this combination of functional groups, the alkene with the alcohol directly attached to the alkene carbon, is called an enol because it's an alkene and an alcohol. This is not very stable at all. This is going to rearrange the instant that it forms. So what it's going to do is sort of shuffle around the location of one of the H's and the location of the double bond. And this is actually an equilibrium that favors the product side most of the time. But what it's going to do is, if you ever make an enol here, it will immediately rearrange to this instead. All right, so if you look, this is technically a structural isomer of that form over there. It's got the same number of atoms, it's just changed what's connected to where. This is called the keto form. This one is technically an aldehyde, but I guess when they were figuring this out, it was going back and forth between some kind of enol with more R groups on it that was making a ketone, so the name kind of stuck. So even though this is not technically a ketone, it's still the keto form, and this is the enol form. Okay. So this whole step is called the keto-enol tautomerism. And tautomers are structures that have more or less the same connectivity, just you're moving around H's and double bonds. I guess I should say mostly the same connectivity. So this thing, as soon as we make the enol, is going to tautomerize. To the keto form. Okay, so the exact details of that are going to vary depending on circumstances. We're going to look at an acid catalyzed and a base catalyzed version of this because one or the other will pop up depending on what the conditions are that we made the enol in the first place. Like if we did an acid catalyzed reaction to get to the enol, it's going to go through the acid catalyzed mechanism to rearrange itself to the ketone. If we happen to be in base when we made the enol, it's going to do the base mechanism to get there. All right. So good question. In almost all cases, the enol is unstable and unfavorable and will immediately rearrange. Give me just a second here to get the camera fixed. Okay. So the keto is almost always favored. Except we've actually seen a few structures that could be described as an enol that are stable enough to isolate. So things where you've got a big motivation to have a double bond between two carbons. So this thing, technically, that's an enol, but it doesn't really like going to the keto form of itself very much. That would be what it would look like, but we're going to be covering aromaticity pretty soon here, but aromatic rings are a huge incentive for this thing to stay in the enol form. We'll also see later on things where if you've got two carbons with oxygens on them, two carbons away from each other, this thing, depending on exactly what's going on, might be kind of close to even. In terms of the keto versus the enol form. And that actually comes down to hydrogen bonding a little bit. Okay, but most of the time, unless there's something special going on that really gives it a motivation to have the carbon-carbon double bond or to have an OH in particular, most of the time keto is better. And you can actually sort of rationalize that to yourself. We didn't spend much time on it in my OChem 1 class, but there's this table of bond energies, I think like way back in chapter 1 or 3, I want to say. And if you go through and add up the actual bond energies for like carbon-oxygen double bond and carbon-carbon single bond versus the other way around, carbon-carbon double and carbon-oxygen single, it turns out that you just have more stable, like more negative bond energy total when you have the carbon-oxygen double bond. Unless there's something weird or special going on like with these two cases. Okay, so, sorry, question? Okay, cool. Mm-hmm. Oh, yeah. Mm-hmm.
Is this like keto-enol formation what makes alkyne hydration characteristically irreversible?
It is, yeah. Mm-hmm. Yeah, so as soon as you get the enol, it just shifts around on you and you get to the ketone, and then it's very unlikely that you can sort of work your way back to the alkyne. Yep. Mm-hmm. Okay. So let's look at the mechanism for how to do this tautomerism before we start working it into the actual alkene addition mechanisms that we're used to seeing. Okay, so acid or base are our two options. But they both need to accomplish the same thing. So to sort of look at what we're trying to do overall, okay, so we're trying to get from here to here. Okay, so what we need to do is add an H here, and we need to remove an H here, and then we also need to shift around the double bond location. Okay, so we got three things we got to accomplish to make this work. If we're doing this in acid, which of these steps do you think is going to be the first thing that's going to happen? Adding an H or removing an H? Adding an H, yep. So we're going to add a proton first. Okay, so this is actually going to look quite a bit like acid catalyzed additions to alkenes, because it pretty much is. Here's our H+. I'm leaving it very vague as to where that's coming from because I haven't really specified any other reaction conditions, but we'll cover some specific cases after this. So the alkene can come out, attack a proton. If that were all that happened, I would be getting a plus charge on this carbon, right? Because that's kind of how alkene additions work. If you're doing it to acid, you end up with a carbocation on one of the carbons. Similar to what we did with the bromine over here, though, as soon as I get a carbocation on an atom with a lone pair having thing right next door, I can actually kick the lone pairs down and stabilize it immediately. So I can show it this way. Or what's a lot more likely is these lone pairs are going to kick down and immediately get this, which is good because that actually takes care of my moving the pi bonds around step as well. I now have no carbon-carbon double bond, but I do have a carbon-oxygen double bond instead. All right, so then the last thing that needs to happen is I'm going to pull the extra H back off of the molecule, but from a different location. So I'm going to draw this out a little bit. So this is where something would come in and pull that H off. And again, I'm okay with ambiguous deprotonation. And that just goes onto the oxygen, those electrons. So that gets you there. Okay, so questions about that one? Yeah?
So in these conditions, would that base pull proton off be water, or would it be base from the acid even though it would be weak?
So you could do either. It kind of depends. Like I haven't specified like what the other actual reagents are that are present. This is just like, yeah, whatever reasonable base you have around at this point would come in. So if you've got water around, it could be water. It could be the conjugate base of whatever you took the proton off of in the first place, which is kind of why I leave it vague a lot of the time. But yeah, as long as it's not super unreasonable pKa's wise, you can show whatever. Okay. So any other questions about the acid mechanism for this? All right, cool. So then in base, we're going to add a proton or remove a proton first? Remove a proton, yep. And we know which proton we need to remove to get where we're going. So we're going to have OH minus come in, take the H, kick that over. And that gets us to here. And then and I guess in this case I am being a little bit more specific about what base I'm using. If you've got OH minus around, which you do happen to have for the base conditions we're going to be using, it's going to deprotonate with that, which would actually generate water as a byproduct here, which can then get its proton removed. So this step here is fairly similar to what we did up here, where the alkene goes out and attacks, and also the lone pairs on this are sort of kicking down to help avoid a carbocation at any point during that process. Okay, so that gets us to the same place. It's just a question of ordering the steps. Okay, so I guess kind of a side note for how to write this up here, I showed it generating a carbocation, which is in resonance to this. It is a resonance form, but it's a pretty minor resonance form. And so a lot of the time, you wouldn't necessarily even draw it out with an actual positive charge on there. You could just bypass this, showing this whole thing entirely, and just draw the arrows going straight from there over to this form. And that's actually probably a better way to draw it, because usually you don't want to stop at a minor resonance form on the way to what's most likely to be sort of the dominant intermediate for that step of the reaction. Okay. So other questions about that? Okay, cool. All right, so now what we're going to do in the last 5 minutes or so is take this mechanism and plug it into stuff that we already know happens on alkenes. Okay, so acid catalyzed hydration. We're going to look at this alkyne, and we're going to change the reagents up just a little bit for reasons that have to do with transition metal chemistry. But so when we did this to alkenes, we just did H2O, and H2SO4 was one possible way to set this up. There were a bunch of other options, like writing H3O plus or H2O and acid catalyst. And any of those would also be a good way to write this. But we are also going to add a little bit of mercury catalyst. This turns out to just make the alkyne a little bit more accessible mechanism-wise, but I guess we won't really get into the details on how that might work until later on. So for now, unfortunately, it's just kind of, it's written on the arrow and we don't really explain why. Okay, so that gets us Markovnikov style addition to this enol, which is very short-lived because that immediately is going to rearrange to this. And I guess if you want to draw the H's explicitly, you can do that. Okay. So then the mechanism for that one is going to be shown the same way as it was for alkenes, where you have the pi bond goes and attacks and gets protonated. And that gets you the carbocation, which then the water can go attack. And then you just have to neutralize the charge on the oxygen. Which gets you to there. And then from here up to the keto product, it's the acid catalyzed mechanism. Okay, sorry, I'm squished up right at the edge of the board here, but that says acid catalyzed tautomerism. So at this point, you would just plug in the entire acid mechanism from up there. Okay, so it helps to sort of think of it as two separate chunks. You go through the regular old alkene addition mechanism, just it's on an alkyne, and then you get to here, and as soon as you get to here, things go sideways a little, and the whole thing rearranges on you, and then you end up with a carbon-oxygen double bond. Okay, so for this reason, we're not ever going to be able to add two equivalents of water to our molecule like we did for HBr, because as soon as we add one, it gets this far and then it immediately does something else, so you couldn't have added a second reagent in that time. So in other words, the tautomerism is always going to be faster than the addition of a second reagent, of a second equivalent of whatever you're adding. All right, so other questions about that one? Okay, cool. So that's a good place to stop. So I'm going to wrap it up there and then do the anti-Markovnikov one next time.